Good afternoon, everyone. This is the third lecture for CS329A. Today we'll be covering self-improvement techniques with verifiers, and we will have three presentations. All the presenters, can you raise your hand so that I know you are here? Awesome, thank you. So just to go through the logistics, there's one slot that opened up on Friday because some student dropped. So if you're still trying to sign up for presentation or want to move your name, you can sign up for Friday. For the discussion questions, submit them in Gradescope by the deadline. Post project milestones, just to remind you, the project proposals will be due next week, Friday, January 24th. For the API credits, we posted a Google form in Ed today. We'll work with the teams to get the credits added after the add drop deadline. So you should get them 25th or 26th, something like that. In terms of office hours, so most of the questions and answers are getting posted on Ed. And the office hours, Azalia has her office hours and I have my office hours on Friday. And John and Mert, the TAs, have their office hours on Monday, Wednesday, Tuesday, and Friday. So take advantage of that. And then one more question. So are there people here who are not yet registered and are still very excited about taking the course? It might change. For the TA office hours, those will be regular office hours. So today we are going to cover three papers. Let's verify step by step, training verifiers to solve math word problems, and Math Shepherd. I believe this is the order in which we will go. So let's get the first group up. Thank you.
So the motivation for this paper is simple. LLMs hallucinate a lot and make logical errors. And especially in math problems, this is a big challenge because even if in one of the steps, the LLM makes a mistake, it can derail the entire solution. So the solution that the authors have come up with is to basically produce a reward model that can assign a reward to each solution that an LLM generates. And then out of multiple samples that an LLM might generate, the one with the highest reward is chosen as the final solution for the problem. So the focus of this paper is the math benchmark. This is a slightly more challenging data set than GSM-8K, which was used in previous work. It contains competition math problems, and we'll see a few examples. So some of the critical contributions of this work, firstly, it highlights that a process reward model is more advantageous and offers better performance than an outcome reward model, and we'll see examples of what these are. Secondly, it emphasizes the benefit of large-scale data collection. It also introduces this method called active learning, which is a method of selecting highly valuable problems that can be human labeled. And finally, it open sources a data set called PRM 800K, which is a large data set of human labeled stepwise scores that can be used to train process reward models. So let's get an understanding of what this method really does. So firstly, we start with a math problem, and then it is passed through a generator, which could be an LLM like GPT-4. And then this LLM would generate a solution, which would contain a lot of different steps, and then the final answer. So in an outcome reward model, what we do is we assign a reward to the final answer, which is quite straightforward because we know the correct ground truth answer to that problem. So we compare it against the final answer generated by the LLM, and then we can assign whether that answer is correct or not. Using this, an ORM can be trained. So essentially, you provide the entire solution to the outcome reward model, and then it predicts the probability with which the final answer to that solution is correct. Now, to train a process reward model, we want to look even deeper into the solution and figure out what are the scores we can assign to each step in the solution. So to do this, we make use of human labelers who would go in and assign a reward to each step in the solution, saying whether that step is correct or not. And using this data, we can train a process reward model, which would essentially assign a probability to each step in the solution being correct or not. Now, the final reward for this solution can be computed as the product of probabilities of each step being correct. So let's do a deep dive into how human feedback collection works. So in this work, they have collected a very large amount of data. So they've gone through 12,000 math problems and multiple steps for each problem, or multiple samples have been collected for each problem, leading to an overall number of nearly 800,000 steps that have been labeled in this process. And this is the data set called PRM 800K, which is now open source for future work. So essentially, they use this process called active learning to choose valuable solutions for the problem. The way this works is the most naive way of selecting samples for labeling is to just ask the LLM to generate a large number of samples and to randomly give all of them to the human for labeling. But what they've done is they've selected samples from this called convincing wrong answer solutions. What this means is they take solutions which have the wrong final answer, but have been assigned a high score by their previous best PRM. So the idea is there may be solutions that look right, but may end up having the wrong answer. And these are the problems that are labeled by humans to be more valuable for the PRM to distinguish between good and bad steps. And each step is given a label which could be positive, negative, or neutral. So now first we talk about large scale supervision. In this model, the generator is a GPT-4 model, and they've not made any modification to the generator, so they just use the model as it is. And the ORM and PRM are fine-tuned from GPT-4 models. So the fine-tuning data is quite simple. For the ORM, as we discussed, you have a generator sample and a score, which is based on the final answer, saying if the final answer to that problem is correct or not. For the PRM, you have the generator sample and scores for each step in the solution that have been provided by humans through the human data labeling process. And in the fine-tuning process, the task of the model is to predict whether each step is correct or not in the case of PRM, and for the ORM to just predict whether the final overall solution is correct or not. So at the bottom, you can see an example of how the PRM has kind of predicted scores for two different solutions. The one on the left is actually correct, and you can see that all of the steps have been labeled as correct by the PRM. And in the second case, you can see that some of the steps have been wrongly labeled, right? So this is quite advantageous because using this, you can not just figure out that the solution is wrong, but also pinpoint where in the solution something has gone wrong. Now, there is a challenge with this large-scale data collection process. As you may have noticed, the PRM uses active learning, which is, you have convincing wrong answer solutions. But you cannot use the same strategy for collecting data for the ORM, because then you would end up with only wrong answers and no correct answers in the data set, which means the model can get biased. So what happens is for the ORM, they do a random sampling wherein you have an equal number of correct and wrong answers, whereas the PRM only has wrong answers, but which have convincing wrong answer solutions. But this causes a difference in the data that is used for training the PRM and the ORM, which makes this comparison kind of unfair. And another issue is that the ORM may contain false positives. So there could be solutions which have the wrong solution, which is wrong steps, but they end up with the right answer, the right final answer. And this means that the quality of data for the ORM training is a bit bad. So to make this data comparable, what they've done is they've created a smaller scale model. And to obtain fine-tuning data for this small scale model, they use the PRM that was obtained from the large scale supervision process to basically assign rewards to both the outcome reward model and the process reward model. So using this, the generator here is 200x smaller than GPT-4, and they've used the PRM for labeling and creating data for fine-tuning both the models. So as I mentioned, the difference here is in the data collection process, wherein instead of human labeling, they've essentially used PRM large for labeling the stepwise scores. So as we've seen, there are three main advantages to using process supervision. Firstly, this credit assignment, that is, it provides precise feedback on where the error has occurred in each solution. Secondly, we can say there is AI alignment because given that the fine-tuning data for a PRM is initially collected from humans, it encourages the model to produce more interpretable reasoning, which is more human endorsed way of thinking through a math problem. And finally, there is an advantage for PRMs over ORMs in the sense that we can avoid false positives that result from wrong steps leading to the right answer by chance. So now let's have a look at the results. The one on the left is for the large-scale PRM and the large-scale models, and the one on the right is for small-scale. And in both cases, we see that the PRM outperforms the ORM and majority voting methods. Secondly, the performance gap widens as n increases. So as the number of solutions that are collected increases, we see that the performance gap widens. And it's even more encouraging to see that the performance of the PRM does not plateau at large n. So which is indicative of the fact that if we were to sample even more, we could extract higher performance from the process reward model. And the authors also noted that there were some problems for which less than 5% of the answers were correct, and yet the PRM was able to pinpoint those correct answers. So that really indicates the ability of the PRM to figure out the right set of steps and the final answer. There is one more, there is one more kind of observation from the authors in the sense that there is out of dataset generalization. So this a model was entirely trained on the math dataset with math problems, but they noticed that on other domains like calculus, chemistry, and physics, the PRM does do fairly well. So it can moderate a decent amount of distribution shift.
Thank you, Emil. So let's go over the strengths and weaknesses of this work as a whole. So the first of all, like it emphasizes the benefit of process supervision over like outcome supervision, and like that was like basically this idea came out of this paper, and like after that, like a lot of follow-up works like emphasize that. And another thing is, so like accuracy is one thing that like everyone cares about, and like this work was the first one that could achieve like relatively much higher accuracy compared to the previous like works on math dataset, which was like one of the hardest dataset at the time. Nowadays it's like pretty much solved, but like back then it was a great achievement. And also they introduced the PRM 800K dataset for research, and like that allowed like many follow-up works to like fine-tune PRMs and also like come up with other techniques based on like process supervision. And going over the weaknesses of this work, we can mention that basically collecting all human annotations, this is not a scalable approach. Basically, they also mentioned that they hired a lot of like annotators to go over all the intermediate steps and label them. And like and also they emphasize that like scaling the amount of data that you have is very important, and at the same time like human labor is a barrier for like scaling it much higher. And basically another thing is like the quality of your PRM is dependent on the quality of the annotations that you can collect from the humans, and like this is not something that we ideally would want, and we want to have a systematic way of telling whether the labels are correct or not. And last but not least, these labels that you collect are model and data set dependent, meaning that, for instance, like not necessarily the labels that you collect for the solutions generated by GPT-4 can be applied to another model, because like maybe another model is making like different kinds of mistakes. And like this process supervision that you are training is kind of optimized for GPT-4 and specifically for this like math benchmark. So like ideally we would like some other techniques that can transfer between different models and data sets. So with that, let's open up to discussions. Like similar to previous session, we can have like 2 to 3 minutes. You can think about the questions, then we can talk about it together.
Okay, the lecture slides are uploaded on Canvas if you folks want to track that. And after that, I will let Zimin, Yifeng, and Winnie present.
Before the time was the chain of thought was published. So at that time, like the LLM's ability to solve the math problems are still like relatively weak. So people want to to enhance the LLM's ability to solve math problems, and they need to find a suitable benchmark. And so we find like the most benchmarks at that time are still for the other tasks, like the language understanding or like the QA. And also, like for those benchmarks for the math problems, and they are sometimes like low qualities, and sometimes they are high qualities like the math benchmarks, but it is too difficult for the LLM to solve. And also, like they most of them, they lack the intermediate reasoning step. They only provide like final answers. So the main contribution of this paper is that it has proposed the GSM-8K dataset. So from this graph, we can see that since it was released, it is still like widely used nowadays. So that is because, not only because it is like a high quality and high diversity dataset, it's also because it's focused on the multi-step reasoning, because we want to like evaluate the LLM's performance like after each step was performed. And for the second contribution, so let's consider a scenario when we are trying to take the exam. So if we try to take the exam with no reference, and so like at the first glance, like we usually like do very badly at the exam. However, like when we're trying to like use a verifier to verify our answers of the exam, so at the second time, usually like we will do like better for the exam. So this is like the second contribution, which is like using the verifier can significantly enhance the performance of the LLM to solve the math problems. Actually, it has shed a light for a lot of the following research, like people trying to build a robust verifiers instead of fine-tuning the models.
Yeah. Then we have come to our methodology section. So for the methodology, they first do a baseline, which is just to fine-tune. So people might think about why don't we just maybe call some ChatGPT models to do some prompt like engineer at that time? That's because they are just don't exist at that time. The ChatGPT, they don't exist. So for these models to perform great, they must perform some fine-tuning on this type of math data set in order to obtain some kind of the reasoning ability. So at that time, the baseline method is just fine-tuning. And then what they want to do on top of fine-tuning is that they build a verifier. So they want to improve upon the fine-tuning baseline. And what they do, how they do this is by training verifiers to judge the correctness of the model completions. And then at test time, they want to generate many candidate solutions. And then they rank them based on the verifier score. And they choose the ones that with the most promising verifier scores as a final answer. They show that this can greatly improve the performance. So this is how we train the verifier. You can see that we have three components in our like sentence or in our maybe data: the question, the solution, and labels. So in the generator phase, definitely we have no score because we are just starting from scratch. So we just have the question and like the solutions. And then in the that's for the train generator, right? We have the question like solution. And in the second stage, when we have the generator ready, we can have like the question and the solution together. And then what we want to do is that we want to find the score for different solutions. So how we do this is like we generate 100 solutions for human to label whether they're correct or not just by looking at the final answer. We don't like see like whether they have correct intermediate results. We just say like if they have the correct answer. If they have the correct answer, we will give like a label of 1, or else we give a label of 0. We just want to see like if they're correct or not. And later in the inference stage, we will also put our when they are trying to generate the solution, we are trying to predict their correctness based on this score. We can see that then the score ranging from 0 to 1 like indicates our belief on what percentage where they do this question correctly. So they have proposed like 2 different verification applications. The first one is like very easy to see. It's just make a single scalar prediction condition based on the entire generated solution. That is, you have a sentence, you have a score. You have a sentence, you have a score, based on like whether it's correct or not. The second one is actually a little bit like tricky to think about. It's like actually making a scalar prediction after each token in the solution. So that is, instead of like trying to map the sentence into like a score, we're trying to like map every generation step into a score. So when the final solution is correct, we just assign like the correct score 1 to all of these like generated tokens. And when in the inference stage, actually the final solution score is like based on the score after the last token. So when we have finished generating the solution, we just take the last token score as our final prediction of whether we think the whole solution is correct or not. And here is like an example realizing like the effectiveness of the token level solution. So we can see that And the red one means that we believe like the score is low, which is like the verifier thinks that it will perform the question incorrectly. And the green one is meaning that it has high score. So you can see that although they start like the first answer, they perform like a few maybe bad like steps, but in the later like they move to the correct track. And then our verifier thinks that it is great, and the final answer is actually great. The second one, they first maybe propose some great tokens, but later they come to some incorrect path. So the red token means that the verifier thinks these tokens are not great, and based on the final judgment, we predict it as an incorrect solution, and actually it is. So yeah, one reflection could be nowadays like maybe it's not necessary to train the verifier anymore. We can just like use some agentic approach, like we try to use one model as a verifier, whether like there's another model as kind of the generator. So I think this could be some kind of remind me of the agentic approach of kind of reflection, because we're just using the model. Somehow we can use this reflection ability to like reflect the answer for themselves to like further improve their answers. And there are some like interesting result findings. So this one is like for baseline. I think this is quite straightforward. So with like better training data size and like with more training data and with like better model size, the relationship between like the performance and the training, these matter approximately follow like a log linear trend. This kind of insight into some kind of scaling law. And the second one is like the verification is like not benefit for smaller data set sizes. And we think that may be because of like the overfitting is like very obvious in this kind of small data set. They're just trying to like memorize their answers based on like some of like their memorized patterns. They do not like generalize well to like larger data sets. And with sufficiently large data sets, verifiers actually provide a significant performance boost. Yeah. And later there is like verification applications. We see that token level verifier is still improving tasks training, while like the solution level verifier quickly shows signs of overfitting. That means like the token level prediction, although maybe a little bit tricky to train, is like performs better generalization for more tasks. And for here, we find like the large model objectives actually help our verifier to learn better predictions. This is because better understanding of the language model distribution could help them to judge whether the answer is correct. And there's also another application study they want to see like based on the same like total model size. Is it better to have big generator and small verifier, or like small generator with big verifier? And the results shows that have a big generator and small verifier is better than having a small generator and big verifier. And they also do some test time compute. I just moving fast because we have limited time. So I have a question. How about the big verifier? That is actually the best. Yeah, we can see the big verifier and big like generator. That is the best, and then followed by the like small generator and big verifier, and followed by big generator small. Oh, sorry. Yeah. It's second is big generator small verifier. Yeah, it's the like image on the left. Yeah. And that is like they do some like how many candidates they want to choose, and how the number of completions, like because we mentioned that we want to like rank the completions based on like their verification score. That is, if we generate more verification, what is like their their final accuracy? We can see that when we are using the number of 400, it is the best. And the last one is like regularization. Yeah.
So here they are actually, as they increase the number of samples in majority voting, they are actually seeing the solve rate go down, which is a function of what?
Yeah, so actually, I think when they're trying to generate like more ones, there are some seemingly correct answers that are verified by verifiers, but they actually turn out to be incorrect. So I think that's the reason why increasing the number of candidates do not always lead to the boost of performance.
So this is almost suggesting that PRMs that come later will kind of solve this problem.
Yes, we have similar insights here. And here, localization, yeah, they're trying to solve the overfitting. And we find out using dropout with solution level verifiers can reach a similar performance as token level verifiers. So that means using dropout combined with like solution level verifiers is like kind of prevent it from overfitting. So that means that regularization is useful. Yeah.
Yep, with that, let's go into some strengths and weaknesses of the paper. So even though it's a relatively older paper, a lot of the ideas are actually still relevant. For example, the paper that was presented just now is we just talked about like how there are a lot of ideas that are interconnected. And then there are also other things that this paper proposed, for example, how you regularize a verifier using, say, like a language modeling objective. And for example, this idea has been used in other following words such as, generative verifiers or, reward model that use language modeling objective as regularization. And then another interesting thing to think about is like the granularity of the verifier. We talked about outcome and process verification. So this paper seems to propose that token level would actually be a good option. So there's also some future work that looks into that. And then one kind of weakness or things to consider is the generalizability. Since we have such a paradigm shift from fine tuning to having one model that can shoot shots. So having a verifier that works well after being fine tuning on one math benchmark is kind of less valuable right now. So it will be interesting to think about whether this approach is actually generalizable to other domains, be it other math benchmarks or even other reasoning benchmarks, or even outside of that, domains where whether there will be domains where verification is actually no easier than solving the problem. For example, you can imagine, problems that require retrieving facts. If you ask about, what's the capital of US? Like, it's not a simpler task than just answering the question directly. So it's interesting to think about whether verifiers is applicable in all kind of domains. And then I'll quickly mention, since GSM 8K is also like a significant contribution of this paper, it remains a very popular benchmark because of the multi-step reasoning component that we mentioned, but it's a relatively old benchmark, and we see a lot of saturation, for example, in this plot that you can see different math benchmarks these days, and the proportion of the questions that are remain unsolved, and it's like a few percentage of the problem that is unsolved. So state-of-the-art model actually achieved close to perfect performance on this data set, and there's potential data contamination due to how old this data set is. It could be that this data set and then some training data of current language models. So with that, let's take a few minutes, like 3 minutes, to go into the discussion questions.
So the last paper that we'll cover today is Math Shepherd.
So I do want to lay the ground really quickly about work that has been done prior. Broadly, how math reasoning has evolved is that the first primary technique was just pre-training on large data sets, then fine-tuning and instruction tuning came around with data sets like MetaMath, Wizard Math, etc. Then we saw prompting techniques with chain of thought showing serious performance improvements over just regular prompting. Also things like complexity-based prompting were used. Then the first three kind of show the era of a single language model. Then, as we've talked so far, came in verifiers. Actually, before the very original version of verification in some way was self-consistency or majority voting, where you just sampled multiple solutions and picked the one that occurred the most often. That didn't require another model. But then when we add a second model, we can look at either outcome-based or process-level verification, as we have talked about so far. To quickly motivate why Math Shepherd came about specifically, obviously math problem solving has been very important, and verifying the generated solution, especially if you can give granular step-level feedback, has shown a lot of potential for improvement. But the issue is that collecting the step-level feedback is very expensive. And given that gathering PRM data is obviously time-taking, expensive, how can you automate this?
Awesome. So you guys kind of already got the background on what these outcome reward models and process reward models are, but I'm just going to quickly recap. A reward model is the way in which you look at the samples in a data set and then update your model based on it. To oversimplify, basically, you look at an example. If your model performs great on it, you reward, and then if it performs poorly, you penalize. So for reasoning, there's the outcome reward model, which is simply just based on did your process get the correct answer? And in this case, you sample solutions, you label them, and then you move on. But then there's also the process reward model, which you actually do this for each step of that problem solving process. You then average the scores for each step and you have kind of your overall score. So in this case, once again, simplifying, you'd have an average score of 2/3. In the earlier paper, yeah, go ahead.
One comment I want to make is that here is a summation in the first paper that we discussed. It was a product.
Yes.
And in some places, they've used a minimum operator. So the operator of how you combine different steps changes.
Yes. Yeah. And another thing that actually also changed from the first paper is that in the first paper, we saw that we were labeling like positive, negative, or neutral for each reasoning step. And in this case, research has shown that binary also achieves like a very similar score with accuracy. And so in this model, they just did binary, correct or incorrect. And so the question then becomes, how do we actually come up with these scores? Like, how do we know if a step is good or bad? And so that's kind of the key contribution of this paper. Like Shubhra mentioned, human annotation is pretty expensive. And so the first contribution is that this paper came up with an automatic annotation methodology to basically annotate the quality for the process reward model. And then their second contribution is that they utilize this data, this methodology to evaluate both a verifier and then train and evaluate a reinforcement learned model. So we'll talk more about that later. But first, the automatic annotation. So our earlier question was, how do we like determine the quality of a reasoning step, right? And in the paper, basically, they decided that we'll define the quality by its potential to get to the correct answer. So there's a couple ways that we can do this, but the paper decided that we'll basically continue tracing down past that step. So given a specific reasoning step, let's say that we're on the first step of your mathematical process, you're going to sample n reasoning processes following that step, and then you estimate the potential of your given step based on the correctness of those answers. So just first, I'll show this diagram. So if you see on the right here, or on the left, there's a problem, and then we have the first step, which is S1. And then we basically, in this case, came up with three branches from here, three reasoning processes, and two of the three came up with a correct answer by the end of it. So there's two different types of estimation that you can use to evaluate like if it's a high quality step. Number one is hard estimation, and this is like, do you ever get the correct answer? Like of all of the different reasoning processes that stem from this step, do you ever get the correct answer? So in this diagram, that's yes, you get it 2 out of 3 times. And the second one is soft estimation, which is an actual ratio of how many times did you get the correct answer over how many overall times did you sample. So that's estimation. And then this essentially becomes our training data for the Math Shepherd methodology. Cool. So taking a step back, the end goal of this project was basically to have a model that solves math problems with reasoning better. And so they created this annotation mechanism as a way to generate more improve this reward model. So the first thing that they did is to test this reward model with verification. And then the second thing they did was to actually train their model with reinforcement learning. And they used proximal policy optimization with a step-by-step nature. So they did it for each step in that reasoning process. Cool. So we already kind of looked at both of these data sets today. Math, which is on the right, was introduced in the first paper, and then GSM-8K in the second paper. But just a couple of things about each of these data sets. They're quite different. GSM-8K, like we mentioned, is high-quality, linguistically diverse grade school math problems between 2 to 8 steps to solve, and it's basic arithmetic, but the interesting part is that they're provided in natural language. And the key concept here is that a bright middle school student should be able to solve each of these problems. And then on the other hand, math is 12,000 like challenging competition mathematics problems. So.
So a little bit about the experiments that they did. So for all the models that they evaluated them on a subset of 500 problems from math, just because math itself is pretty big. For each solution, they sampled 256 candidates, and they also ran this whole process thrice just to average the accuracies over those 3 rounds. The models that they used were from Llama, and DeepSeek, but they also fine-tuned all those models on MetaMath, which was one of the fine-tuning data sets that we mentioned earlier. For their experiments, their baselines are majority voting, so just simple like one language model, self-consistency, or majority voting, and then also using outcome reward, or just using ORM. Okay, cool. So results, so there are 3 sets of results. First, there's just using Math Shepherd trained models as like a verifier, where I think the thing I would like to point out here is that So on math, so on the right-hand column, self-consistency actually helps whenever you have like ORM or whenever you have Math Shepherd, versus on GSM-8K, which tends to have easier problems. Self-consistency actually takes down the performance a bit. I wanted to highlight this specifically because I think last class we talked about how majority voting should help easier problems and probably hurt harder problems. So it was just interesting to see that this wasn't the case here, and I wanted to highlight that for like that could be an interesting thing to look at in the future. Okay, so these are the results for verification. They also used Math Shepherd to train a model using PPO. And one like thing to note here.
Can you go back one slide?
Sorry, yes.
Can you go through each row just to compare each of the results? So self-consistency was the lowest score, that's majority voting.
Yeah. So self-consistency so there's 3 separate models. For each of them, we see that self-consistency has the lowest score. ORM then is just like training using only outcome level feedback. If you use self-consistency in ORM, you do see a little bit of an improvement, but in general, we do see that Math Shepherd performs the best because it is giving process level feedback, and it also does that at like a very low cost.
What does it mean to have self-consistency plus Math Shepherd? Because Math Shepherd means that you have process level annotated data, right? So self-consistency means you have multiple chains that need to agree, or just the final answer need to agree?
I think in this case, self-consistency was based on the final answer. So self-consistency plus Math Shepherd was Math Shepherd re-ranking, and then I think maybe self-consistency over the top and out of the re-ranked ones, I believe. Yeah.
Is there any difference between models?
Not really. I think DeepSeek, actually, no, not really. I think maybe size is probably the primary difference. Oh, and then also Lemma is specifically pre-trained on a lot of math data. So it is a math-specific model, which it's probably better as compared to other 34B parameter models, but compared to other 70B parameter models, it does fall a little short. Those would probably be the major differences.
And I believe with the experimentation, they also worked with smaller models. It's not in this table specifically because these are comparing the larger models and their evaluation scores, but they did work. They wanted to showcase that this could kind of work with smaller and bigger models. So they did have the 7B version of Llama, for example.
Yeah, and actually we'll get right to that right now. So for PPO, they did use smaller models, and as we see, the baselines were pretty bad in like the 60 to 70% range, but then when they do add, so fine-tuning does improve. I believe RFT was just fine-tuning with MetaMath. Yeah. And then ORM PPO is again just using like MetaMath answer labels. And then finally, when they use Math Shepherd and step-by-step PPO, that gives the most largest improvements. Although again, I did want to highlight that on harder problems, so on math, the margin of improvement is slightly lower. I don't know if it's like significant that it is lower, but on the right-hand side, top right, we see that there's about like a 2% improvement and like a 5-ish% improvement on the bottom, versus the GSM-8K improvements tend to be larger. This could also just be contingent on the fact that the original performance on GSM-8K was higher. So either of those two could be the reasons, but I did want to point that out. And then finally, this was like, yeah.
Class we were discussing that harder problems should see gains, right?
Yeah.
I think one possibility is that we needed to explore more on harder problems.
Yeah.
We needed to do a parallel search before we could get the gains.
Yeah, that would make sense. I think, there were probably also, I think in terms of compute, they only sampled 256 different solutions, which now that we've seen the large language monkeys paper, you're often searching for solutions at the scale of thousands before you are seeing performance improvements. So that is a good point that maybe searching more would have helped quite a bit. I guess, and then finally having both PPO and verification, using Math Shepherd for both PPO and verification showed the best results. There was nothing particularly notable here besides the things that I've already mentioned. And you guys are generally familiar with the terminology. So if anyone has any questions, I will leave this up for a second. Yeah.
Can you go through the hard estimations, soft estimations?
Yeah, of course.
Yeah. So
Mhm.
when you're generating the n reasoning processes, you have steps S1 to Si in the context, right?
Mhm.
So like if Si is a totally random sentence, like you're trying to solve a math problem, and Si is that Earth lies in the solar system, then Si and Si minus 1 would be having the same relevance to the question.
Yeah, so each of the steps that are mentioned here are stemmed from that original S1. So in this case, like each of like S2, (1), S3, (1), those are all conditioned upon step 1. Does that make more sense?
So I'm saying that like Si can be totally random, and then it will still have the same relevance as Si minus 1.
I see what you're saying. So almost like a really, really bad irrelevant statement is equivalent to like a high quality statement.
Yeah.
Interesting.
I'm not sure
I actually didn't think about that.
So I think the comment that you're making is that you can have irrelevant statements in between, but when you're combining in the process reward model, you will not always benefit from summation. So if you do a min across the steps, then the reward model will be able to filter out such nonsense. So in the papers we covered last week, they were taking a minimum. And the optimal scaling paper actually found that minimum was the right thing to do. So this can change depending on the model, perhaps.
Yeah, and I believe they did take the minimum in this case.
Okay.
When they did the final estimation, they take the minimum to basically account for the weakest explanation process or explanation step.
Cool. I think beyond results, I wanted to talk a little bit about what has been done since, in case someone's interested in a project in this area. Quen released a reward model. So Quen 2.5 is a family of models. They released a 70 billion parameter reward model that they used to train their math-specific model. So that could be something interesting to play around with because it is like a pre-trained reward model that you can use out of the box. There was another work that looked at tree-based preference learning, where they look at, I think they do it, I think it is, so it's binary. I believe it was outcome based and not process based, so that is something to take into account. But if you're interested in preference learning, that could be something interesting. Similarly, if you're interested in preference learning, there is a paper that looks at preference optimization for reasoning with pseudo feedback, where in case a lot of you were wondering, well, I could just use GPT-4o to get like preference labels instead of like either using a formula or using human annotators. That's what this paper does, in case that's something you're interested in looking at. And yeah, so that takes us to our discussion questions.
So let's do 3 minutes.
Mhm.
The class discussion.